This video describes research performed at Kansas State University to evaluate the design criteria used for frangible joints in storage tanks. The research was sponsored by the Pressure Vessel Research Council and the American Petroleum Institute. Storage tanks are widely used to store flammable liquids. This picture shows a typical tank covered by the API 650 rules. It is cylindrical and has a shallow conical roof. As such, a tank is repeatedly filled and emptied. It is possible that the gas mixture above the liquid becomes combustible. If a tank is struck by lightning, or for some other reason the gas is ignited, it is possible for the gas mixture to rapidly burn or deflagrate. This shows a tank fire in Texas that occurred in 1993. Note that the roof has detached from the tank shell, but that the shell has remained intact, allowing the firefighters to extinguish the blaze. Such a controlled failure is desirable. This type of failure is not desired. Here the shell has separated from the floor and the tank is releasing all its contents. It should be noted that this tank had a domed roof and was not designed to API 650 rules. The previous examples showed different ways tanks can fail. API 650, issued by the American Petroleum Institute, gives design rules that are intended to ensure that the roof-to-shell joint is frangible. That is, the failure of the tank is controlled so that the roof detaches and relieves pressure in the tank before failure occurs at any other point in the tank. The API 650 rules control the permissible designs at the compression ring and cover other aspects of tank design. The objective of this research is to review the rules in API 650, focusing on the area inequality rule, the effect of roof slope, tank diameter, and weld size on tank failure. The research program has addressed these questions through a combination of structural analyses, combustion modeling, static model tests, and dynamic model tests. Before proceeding, let us briefly review the frangible joint criteria in API 650. The basic design rule is the area inequality rule, which states that the area at the joint resisting the compressive force must be less than the calculation shown. Other parameters controlled include the weld size and roof slope. The area inequality rule uses static equilibrium to calculate the pressure that will cause yielding in the compression ring before tank uplift.
What I'd like to do is use this scale model to help explain the basis for the API 650 rules. We can imagine we have a tank out in the field, and often this shell of the tank will be resting on a foundation. The floor inside the tank will be resting on a sand base. A logical and reasonable way to prevent failure of the bottom joint is to make sure that the tank does not rise up on the foundation, and so, by rising up, make large deformations in the bottom joint. So our objective is to make sure that the tank does not uplift, and to do that then, we have the downward weight of the tank holding the tank on the foundation. Now imagine we have pressure inside this tank. The pressure on the roof wants to lift up the tank. However, also as the roof is being pushed up, it wants to deform up, and that then puts this, it wants to pull in the top of the shell and put this area on the top of the shell into compression. That's why it's called the compression ring. The intent of API 650 is to make sure that the internal pressure in the tank lifts up the roof, puts this ring into compression, and it then is intended to make sure that this ring fails before the upward pressure on the roof is sufficient to lift up the tank. So that is why the area inequality rule forces the area of the compression region to be less than some value. That area is chosen to make sure that it yields, and then as it yields, it goes into local buckling and then causes failure at the frangible joint. The roof flies off, and the rest of the tank stays resting on the foundation.
It can be shown that small tanks are more likely to experience uplift than large tanks. Of the overpressurizations shown in this figure, the red squares indicate undesirable failure at the bottom joint. It can be seen that these observed failures tend to occur for smaller tanks. These analytical curves emphasize the same point. For large tanks, the uplift pressure is much larger than the joint failure pressure, while for small tanks, the uplift pressure can be less than the joint failure pressure. This is undesirable, since uplift can lead to failure of the bottom joint. Finite element analysis was used to help understand and predict the stresses, natural frequencies, and buckling of the tanks. This shows a typical three-dimensional finite element model. In this case, the analysis shows the deformation of the scale model tank that used stitch welding to attach the roof to the shell. The colors show stress contours in the tank. An important result of the analysis was the prediction that the natural frequencies of the tanks were higher than the expected loading frequencies. Thus, it is valid to use static analysis to predict the tank responses up to the point of tank failure, which is then a dynamic process. In parallel with the structural analyses, development proceeded on a combustion model to predict pressure loads on the tanks. A simplified model was used based on laminar deflagration with a turbulence correction for flame speed. In the first phase of the research, tests were made using statically loaded scale models. The objectives were to observe buckling predicted by the analysis, evaluate yielding as a failure criterion, and verify the predicted effect of roof slope. You will next see videos taken during testing of the two tanks. The first tank had a flat roof, while the second had a slope of 4 in 12 inches.
This is our test of the 4-foot diameter tank with a flat roof. It's made out of 20 gauge metal, and we have the roof pop riveted onto the sides of the tank. What I'll do next is I'll zoom in, and you can see how the pop rivet, how they attach the top to the sides of the tank. What you can see there is the framework that we use to take the displacement measurements of the top of the tank, and you can see the tube going out of the top of the tank that goes to a pressure transducer that we use to measure the pressure in the tank, and you will see there's some strain gauges, and so we are recording pressures, strains along the top of the roof, and we will measure vertical displacements of the roof top.
236, 232, 222.
Okay, this is at 1 psi, and you can see the buckling pattern that has developed. G-Lu claims to have predicted that this should happen at 0.84 psi, and it looks like the displacement in the middle is about 1 inch, which again is pretty close to the prediction for the flat roof. This is about 1.2
Right now, 1.2.
psi, and there is a circumferential buckling happening at the top of the shell structure. 1.3 psi, that place where we had seen the
It reached 1.
buckling before, buckled more. So we saw that happen there. And right now in the test, the pressure is dropping because of a leak. And so we're going to put more water into it. This is a large buckle here now. You can see how it went to the outside in the shell. In radial direction at the buckle. You can see how it came in. This is the tank after the test. And you can see the buckles again. I'm going to walk up. There are 4 buckles at about 90 degrees apart from each other. first buckle. And now we come in. And there's a buckle there. There. And over there. And they all look about the same. We have changed the test setup a little bit from the last time. And I will show you how we intend to regulate the pressure, this time using air pressure supply with a pressure regulator on the input air that will control the pressure in a tank that then feeds water into our tank. We will be reading the pressures still, though, using a manometer, and we have a tap at the top of the scale model tank that we'll use. Here you can see us taking initial readings of the displacements around the periphery of the tank roof. 2.03. Here you can see the pop rivets that attach the roof to the shell. Okay, for posterity, we're going to have the analyst predict what will happen in the test before it happens. So when is it going to fail, Zilu?
The plastic yielding started from 3 psi, and there won't be any buckling until 6 psi.
Okay, so we expect. Okay, so we don't expect to see those elastic buckling deformation. Now the test is at 1 psi or 2 inches mercury. 0.75, 0.59. And we are taking the measurements of the displacement of the roof. 0.41. As I said before, what's interesting is that, as predicted, we see no elastic buckling at the top of the roof. 2 psi, and what this is to show you is that there is just about none of the, or no, elastic buckling occurring. So you can see it's a smooth, round surface. And also there's not much deformation of the tank top, and we'll show you that next. See, we lay the flat edge on it, and that's about how it was when we started the test. There is a little bit of deformation going on around the compression ring. Just a second and I'll zoom in. You can see just a little bit of the uplift around the ring that's happening at the top of the shell. And we are worried that the bottom is going to fail in the tank right now. There's quite a bit of liftoff going on, and some of our screws are coming undone at the bottom. So we're going to take some fast readings. The very noticeable thing that has happened is there have been local buckling just very close to the rim, or to the top of the shell. I'll try to move around, and so you can see these local buckles. There's one there.
No.
Yeah, okay. So very small local buckling.
They're down.
We're loading it up now above 4 psi. The thing is just about ready to fail.
9.1.
You can see the buckles forming. There that one goes. There it goes. All right.
Oh, yeah.
Perfect.
Okay, 9 point, the volume increase drop. 9.3, 9.4,
Now,
another one's going.
Where's that one? 5 inches mercury, about 4.
9.7.
And you can see there's buckles forming all around the periphery now.
Yeah.
Local buckles. This is the yielding buckling going on. There's one formed there.
10.1.
Okay. The first buckle again. See, the buckles are forming all around. This is about 5 psi. At the end of the test, it reached about 5.5 psi max, which is 11 inches mercury. And you can see here the buckles again. And I'm going to go and show you from the side. What's interesting here, of course, is that as we expected, all the deformation happened around the periphery of the ring, or the periphery of the roof for this tank. One thing completely different from the flat roof was the flat roof only had 4 major buckles form, and they formed at one point, then 180 degrees away. Here we had multiple buckles forming at the same time, and you can see how they're spaced close together, but also the only activity is right at the juncture of the roof to the shell. Team at the end of the test.
Not all the team.
Looks good. Good test. So it did what we thought it would do. The yield stress is a little bit higher than what we assumed when we found that in the other test too. When Zilu said 3 psi, that was assuming 32,000 psi yield. It actually looks like the yield stress for this material is higher than that. But it looked like it, about 5 psi, we really had a lot of yielding going on.
The scale model tests provided 3 important results. First, even though elastic buckling occurred, it did not cause failure. Second, failure initiated with yielding of the compression ring, as assumed in API 650. Third, the analyses successfully predicted the pressures at which yielding occurred. The second phase of the research focused on dynamic testing of larger models. These tests were performed by igniting an air-methane mixture in the tanks. The tests allowed us to observe dynamic failure of the tanks and to verify the combustion model. The following video shows the preparation of the tanks for testing. 2 tanks were tested, one with a standard continuous weld and one with a stitch welding attaching the roof to the shell.
This is the one with the continuous weld on the roof, although you could not tell that from this point. We're looking at the roof. But we're going around the top of the roof. This is the weld. That is the center beam that's just going in front of the middle of the camera. And you can see how it looks. This tank is 8 feet tall. I'll zoom out. And you can see how the rafters go in to the center beam, which then has a support on it that they are attached to. It's made in 2 4-foot sections high. This is the weld along the center of the tank, and what you see now is the strain gauge connectors. And the strain gauges are mounted up here, up in the top of the circumference. And there's corresponding locations on the outside of the tank, so we can hope to capture some buckling and bending effects during the test. Okay, here we're in the evening now and we're still running static tests. There's the crew. Okay, yep, Jerry. Asif, look up. There you go.
It's almost sunset.
Yeah, it's sunset. Okay. Mark. And look, there's the sun going down. Okay, we've been successful getting 1 static test. We're going to run a couple more, and then we're going to run a dynamic test tonight still. Well, here we are at night. We're running the 3rd static test, and just looking at the data. Actually, we've already finished running the test. Just looking at the data, make sure it's good data before we go on and try the dynamic test. Okay, here's Jerry Bittner putting up the PVRC sign. There we go.
In preparation for the dynamic tests, open-air tests were done to make sure we could successfully ignite the air-methane mixture. A large balloon was used to control the ratio of air to methane. A spark was used to ignite the mixture.
This is our 2nd try at this. We're out here looking at the balloon, and Jilu has now gone to the button. Okay, and I'm going to lower my arm and we'll see what happens. What it looks like afterwards. You can see here the balloon just kind of tatters up. It's a little bit hard to see, but there's 2 prongs going in to the spark plug, and it looks like it worked pretty good. We get a pretty good spark.
1 open-air test was performed at night. Remember that each video frame is 1/30th of a second. You will see that it took about 1/3 of a second for combustion of a balloon with an initial diameter of 9 feet, verifying the deflagration assumption in the combustion model.
Yeah, they hit us. It was exactly 12 midnight.
You will now see the same test frame by frame. The first tank tested used standard design practice with a continuous weld attaching the roof to the shell. You will see the test site, which included the data acquisition equipment, the air methane mixture controls, and the shelter for people and equipment.
Okay, here's where people stayed last night. And it looks like everything's here. There's the car. And we're going to get ready to go. It's about 7:20 right now. And off in the distance, our tank. There you see it, both of them. And this is the one that's going to go.
Behind the truck, you see the shelter for the data acquisition computer and the experimenters. Data acquisition included measurement of strains, as well as videos and a high-speed camera. Failure was initiated by local inelastic buckling of the compression ring, as can be seen more clearly in the following frame-by-frame view. This is the same test viewed from the north.
Here, it looks like it went off just like it's supposed to. And we're going to walk up and look at it right now. Hope we have the data. That's one that we don't know yet. Oh, look at that. Just perfect. Just opened right up. Nothing happened at the bottom. But it's buckled up there. I think we'll see exactly what we're looking for in this tank. Full buckling. Look at that. Going on. See how it moved in? Okay, here's how it looks now. It looks a little bit different, but it's still pretty neat. And we're going to open it up and look inside. We're on the top weld first, starting at the strain gauges, and you can go around and see how it's split open. There's first rafter. See a buckle there. Second rafter. Some more buckling. That rafter buckled. And you can see the weld is split just about all the way around. There's still some good welding. That brings us back to the beginning. Now we'll look at each of the rafters. This is the rafter right above the manhole cover. It's buckled, as you can see. The second rafter, and it's buckled at the end. The third rafter, still up there. The fourth rafter, buckled on the outside there. Fifth rafter. And the sixth failed. It was bolted to the top, and you can see there's the bolt that pulled out. Just keep walking around this. This buckle is not at the rafter, but that is the big buckle that did the failing.
The second tank used stitch welds to attach the roof to the shell. There were 18 stitch welds, with each weld being 2 inches long. This test was performed to evaluate one possible alternate approach to frangible joint design. You will now see the same view, frame by frame. This is the same test viewed by the high-speed camera. Notice the scalloping of the roof before failure. Also notice that much less tank motion occurred during this test as compared to the previous test of a continuously welded tank. This is because the peak pressure in this test was 5 psi, while in the continuously welded tank it was about 10 to 15 psi.
Yeah, the roof fell off just like we thought it would. Good. You can, well, look here and you can see that each of the welds unzipped just like we thought they would. Okay, it's a little bit hard to see up here. I'm going to walk forward. And see how it pulled in? Just where we wanted it to, and the welds unzipped each weld. Just perfect. See, the buckling pattern looks just like we predicted. Look at that. I'm walking around here.
People that would have walked over.
All right.
It's not going to blow me away, is it?
Okay. Okay, look at that. Just slicker than anything. Yes. Just right. Okay. And it was really neat. Look, the rafters are still in place. A lot less deformation of the top of the tank. Just beautiful.
Dynamic testing confirmed that combustion occurred by deflagration. This means that the pressure loading rates on the tanks are slow enough that the tank response is essentially static up to the point of failure. Failure of the continuously welded tank initiated due to local inelastic buckling at the compression ring. Importantly, even though failure initiated at a pressure of about 5 psi, the peak pressure is believed to be between 10 and 15 psi. Failure of the stitch welded tank occurred by tearing of the stitch welds. Again, although failure initiated at about 1.5 psi, the measured peak pressure was 5 psi. The main results of this study are that combustion occurred by deflagration, elastic buckling did not cause failure, and that failure initiated with yielding of the compression ring. Yielding is followed by a plastic instability in the joint. Importantly, the pressure continues to rise after initiation of failure. Eventually, as the roof continues to detach, sufficient venting occurs to reduce the pressure in the tank. This means that the peak pressure can be much larger than the pressure at initiation of failure. Peak pressure controls uplift of the tanks. As such, it is a fundamental parameter needed for failure evaluation. The actual peak pressure is the result of the interaction between combustion, failure, and venting. A coupled model, taking these phenomena into account, is being developed in the final phase of this project. This model will be used to generate design curves giving peak pressure for different geometries and will be available to the designer for use in evaluating a particular design.
Now we are working on the final phase of this project. First, we have a axisymmetric finite element model to calculate the stress and the strain in the tank. And we have a combustion model to calculate the pressure rise in the tank. When the pressure rises to a certain value, which makes the compression ring reach yielding pressure, yielding stress, we say the tank is going to fail. And now we are working on to make a mathematical model of this opening up of the joint, and also try to find out how fast the crack goes. So we can have a venting term and the feedback to the combustion process. So hopefully we'll find out the peak pressure in the tank when the tank fails. And the peak pressure is what we really want. If the bottom can stand the peak pressure, the tank is really going to be safe.
This project was funded by the Pressure Vessel Research Council and the American Petroleum Institute. We appreciate the support of Texaco, the El Dorado plant, Ace Construction Company, and Chicago Bridge and Iron.